The universe drifts on an invisible tide, across gulfs of darkness where galaxies shine like fragile lanterns. Something stirs, not light, not matter, but a force as elusive as breath upon glass. It whispers through the fabric of space-time. An unseen wind expanding the very stage upon which all existence plays. For billions of years it has moved in silence, unnoticed, gathering strength until its presence could no longer be denied. Today it has a name, but not an identity. Dark energy at first. The cosmos was thought to be slowing, gravity holding its galaxies in a delicate embrace. But the truth revealed itself as a paradox. The universe is not falling back inward, but rushing outward, faster with each passing epoch. The stars themselves are passengers upon an accelerating current, carried toward horizons they will never reach. This is no gentle drift. It is a storm, swelling within the void, pressing space. Apart like a great cosmic breath, the scale is beyond comprehension. Invisible pressure builds between every cluster of galaxies, as though the cosmos itself is filled with an unseen ocean, pushing everything adrift. Astronomers measure its strength, not by what it gives, but by what it takes. The distance between galaxies, the faint dying light of ancient supernovae, the echo of the Big Bang stretched thinner with every heartbeat of time. If it continues unchecked, the end will not come with fire or collapse, but in silence, galaxies torn from one another, stars severed from their planets, atoms pull apart until even matter dissolves. A storm that leaves nothing behind. What is this unseen wind, and how long before it swallows everything? In the early years of the 20th century, the universe was thought to be eternal and unmoving. Astronomers pictured a great cosmic stage, vast but fixed, where stars burned without end and galaxies stood as permanent islands in an endless sea. It was a vision of stability, of eternity suspended in silence. Yet, hidden within the equations of a young physicist named Albert Einstein, something disruptive stirred. His general theory of relativity described a universe where gravity was not a force pulling bodies together, but a curvature of space-time itself. And in the language of those equations, the cosmos could not remain perfectly still. Left untouched, his mathematics suggested the universe must either expand or collapse. Troubled by this, Einstein inserted what he called the cosmological constant, a subtle term designed to counterbalance gravity and keep the universe static. To him, it was a mathematical patch, a quiet adjustment to preserve the eternal cosmos so many believed in. But nature resists human expectation, for within a few short years, the universe would reveal itself not as a motionless edifice, but as something alive, dynamic, and growing. Einstein's constant, devised to hold the universe steady, was destined to become one of the most haunting curiosities in the history of science. In the 1920s, a new window was opened upon the heavens. At the Mount Wilson Observatory in California, a telescope of unprecedented scale was aimed toward faint smudges of light, long thought to be nebulae within our own Milky Way. Yet the work of Edwin Hubble revealed something astonishing. These were not clouds adrift within our galaxy, but galaxies in their own right, colossal systems of stars far beyond our own. The universe was suddenly larger, more populous than anyone had dared imagine. Hubble went further. By measuring the light of distant galaxies, he uncovered a strange and undeniable pattern. Their spectral lines were stretched toward the red, a cosmic signature of recession. The farther a galaxy lay, the faster it seemed to move away. Space itself was not static. It was expanding, carrying galaxies outward like driftwood on an ever-widening tide. This revelation shattered centuries of assumption. The universe was not eternal and changeless. It had a history, a beginning, and perhaps a future end. For Einstein, the discovery was a moment of regret. He abandoned his cosmological constant, calling it later his greatest blunder. The equations had spoken truly all along. The decades that followed carried with them a quiet assumption. If the universe was expanding, then gravity, the ancient sculptor of structure, would eventually slow it down. Galaxies pulled at one another across the void. Dark matter added unseen weight, and all the while the expansion should gradually lose its pace. Astronomers expected that cosmic expansion would decelerate, like an arrow fighting the drag of air. Whether the universe would halt and collapse, or coast forever at a dwindling rate, remained uncertain. Yet deceleration was seen as inevitable. For most of the 20th century, this picture held. The universe was expanding, yes, but like a ball thrown into the sky, its upward flight would one day be tamed by the pull of gravity. The cosmos seemed bound to follow the rules of balance and restraint. Few imagined that something else, something hidden, was already at work, shaping the story into one far stranger to measure the pace of this expansion. Astronomers turned to stellar explosions, type Ia supernova. These rare detonations occur when a white dwarf star, the dense remnant of a sun-like star, accumulates too much matter and collapses in a thermonuclear blaze. They shine with a brilliance rivaling entire galaxies, their peak luminosity astonishingly uniform. Because of this reliability, they became known as standard candles, cosmic beacons whose brightness revealed distance with precision. By comparing how bright they appeared with how bright they truly were, astronomers could chart the scale of the universe with remarkable accuracy. In the closing years of the 20th century, teams of astronomers sought to use these standard candles to answer a fundamental question: how quickly is the universe slowing down? They expected to see evidence of gravity's grip, a gradual breaking of cosmic expansion over billions of years. What they found instead would rewrite the fate of the cosmos. The light of those distant supernovae carried a different story. Galaxies were not merely receding. Their retreat was accelerating, as though some unseen hand was pushing them apart faster with each passing epoch. The evidence was undeniable, the data echoing across independent surveys and instruments. Instead of slowing, the expansion of the universe was quickening, driven by a force that could not be seen, touched, or measured directly. The astonishment was profound. Astronomers had set out to measure the deceleration of the cosmos, only to discover the opposite. The universe was behaving as though an invisible storm had been unleashed, stretching space-time itself at an ever-increasing rate. The cosmological constant, once discarded, suddenly seemed less like a blunder and more like a prophecy whispered ahead of its time at first. Disbelief clouded the reaction. The possibility that such a vast mistake had been uncovered in humanity's vision of the cosmos was difficult to accept. Could the data be flawed? Were the supernovae not as reliable as once thought? Teams recalculated, scrutinized, cross-checked, yet the conclusion held. This was not an error. The expansion was real, the acceleration undeniable. What could drive such a phenomenon? Gravity binds, matter attracts. Nothing in known physics could account for a force that pushed galaxies apart with increasing strength. Something new, something wholly alien to human understanding, had entered the cosmic stage. It was given a name not for what it was, but for what it was not. dark energy, a label that held more mystery than meaning, marking the presence of an unknown that now dominated the fate of everything. In 2011, the Nobel Prize in Physics was awarded to the scientists who had unveiled this truth, that the universe is accelerating in its expansion. Their work did not solve the riddle, it only sharpened it. What had once seemed a neat equation of matter and gravity was now a puzzle with missing pieces. 68% of the cosmos appeared to be made of this dark energy, a substance, or property utterly beyond comprehension. Einstein's cosmological constant, resurrected from dismissal, once again became a candidate. But the questions it raised multiplied. Was this constant truly constant? Was it the energy of the vacuum itself, or something dynamic, shifting through time? And if it was real, what fate did it inscribe upon the future? For humanity, the discovery was more than numbers on a page. It was a humbling confrontation with ignorance. The stars, the galaxies, the vast web of matter, all of it, combined, made up less than a third of reality. The rest was hidden, untouchable, yet undeniably there, steering the cosmos on its path. For the first time, the universe was revealed, not as a tranquil sea guided by gravity's hand, but as a storm-tossed expanse driven by an unseen wind. This was the beginning of a new era, where certainty dissolved into mystery, and every observation seemed to deepen the enigma. The expansion was accelerating, and the question that echoed across observatories and journals was no longer what is the universe doing, but what is driving it, and why now? In this revelation lies a haunting symmetry. Einstein, who once inserted the cosmological constant as a contrivance, had dismissed it in regret. Yet the universe seemed to whisper that his discarded idea may have been the closest glimpse of truth. A patch transformed into prophecy, a blunder reborn as vision. The storm expanding across the cosmos carried within it the echo of his equations, reshaped by time, and recast as a force that would challenge every human attempt at understanding. The origins of this discovery mark the threshold of the mystery. A journey that began with a quest for stability led to the revelation of chaos. And standing at the edge of this realization, humanity looked outward and saw not merely the galaxies racing away, but the unsettling knowledge that an unseen hand was shaping the fate of all things. The story of dark energy begins here, in a paradox born from mathematics and unveiled through light that traveled billions of years. It begins with Einstein's refusal to accept expansion, with Hubble's discovery of a universe in motion, and with supernovae whose deaths revealed not slowing but acceleration. It begins with disbelief, with recognition, and with a name that conceals ignorance behind a veil of words. The universe is not just expanding, it is being pushed apart, driven outward by something beyond measure. A storm, invisible yet irresistible, sweeping through the fabric of space-time. Humanity has seen its trace, felt its consequence, and glimpsed its scale. But the nature of the storm remains untold, and the question endures, as haunting as it is vast. What is dark energy, and how long before it reshapes everything we know? The revelation of cosmic acceleration spread through the scientific world like a tremor shaking the foundations of established knowledge. For decades, astronomers had measured galaxies, weighed clusters, and charted the vast scaffolding of the cosmos under the quiet assumption that gravity must be the final arbiter. Every galaxy, every cluster, was a stone in a cosmic arch destined to eventually feel the pull of its neighbors, too slow, perhaps, to collapse. But the supernova data of the late 1990s refused to yield to expectation. Instead of a slowing universe, the numbers whispered of a cosmos rushing outward ever faster, as though pursued by a ghostly hand. Shockwaves rippled through observatories and universities, through conferences and late-night calculations. Some dismissed it as error, a miscalibration of instruments, a misunderstanding of stellar physics. Others sat in stunned silence, gazing at plots of redshift and luminosity that stubbornly refused to obey the equations of a decelerating cosmos. It was as if the universe itself had betrayed their predictions, shattering one of the most deeply held beliefs in modern cosmology. This disbelief carried the flavor of grief, grief for certainty, grief for a universe once thought more comprehensible. Theories that had been long accepted now felt provisional, fragile, like chalk sketches waiting to be washed away by the incoming tide. To many, the accelerating cosmos was less a discovery than a wound, a rupture in the trust between mathematics and nature. Yet for some, that wound was an opening, a door into a deeper, more unsettling reality. And so began the struggle, not only to accept the data, but to find language for the invisible force that was reshaping existence itself. They reached for names, as though naming might tame the unknown. Some revived Einstein's old term, the cosmological constant, once discarded as an embarrassment, now resurrected with a kind of uneasy reverence. Others reached further back into the vocabulary of ancient philosophy, calling it quintessence, a modern echo of the fifth element. Aristotle once imagined as the substance of the heavens. Still others sought refuge in the language of quantum physics, invoking vacuum energy, the ceaseless bubbling of virtual particles flickering in and out of existence. Each name carried with it not just a label, but a story, a theory, a framework for comprehension, yet no name seemed to fit completely. Cosmological constant suggested a timeless, unchanging pressure built into the very equations of space itself. Quintessence implied a dynamic field, evolving with time, perhaps able to weaken or strengthen as the universe aged. Vacuum energy hinted at a quantum origin, but also led toward one of the deepest and most troubling paradoxes in modern physics. In every attempt to name the storm, scientists revealed the enormity of the challenge before them. To describe it was already to confront its mystery. To categorize, it was to acknowledge how little was truly known. And yet the act of naming also gave it presence, shaping human imagination, giving journalists, researchers, and dreamers alike a word to hold on to as they stared into the accelerating abyss. Dark energy, the simplest and most haunting of all the terms, soon eclipsed the others, a phrase both evocative and ambiguous, capturing the essence of a phenomenon defined by absence, invisibility, and power. Dark energy bore a chilling resemblance to another mystery, the vacuum itself. Quantum field theory described empty space not as barren, but as restless, a seething ocean of fluctuations, virtual particles blinking into being before annihilating in the blink of a moment. This quantum foam, invisible yet mathematically inevitable, carried energy, and in principle, that energy might press against space-time itself, driving expansion. To many, it seemed almost poetic that the void, which ancient philosophers imagined as nothingness, might instead be the very force sculpting everything. Yet the beauty of this idea collided with its absurdity. When theorists calculated the expected density of vacuum energy, the result was catastrophic, 120 orders of magnitude larger than observation allowed. This was not a small mismatch, not an error of rounding or a misplaced constant. It was the largest known discrepancy between theory and reality in all of science. The vacuum, in theory, should rip the universe apart instantly. In practice, it was gentle, subtle, almost delicate, shaping the cosmos only across billions of years. This mismatch haunted physicists. Was their understanding of quantum fields fatally flawed? Was dark energy something entirely distinct, hiding in the blind spots of human mathematics? Between the trembling equations of quantum physics and the stubborn data of astronomy, a gulf yawned, a silence filled with doubt, speculation, and awe. It was a silence that demanded patience, for the answer, if it existed, lay beyond the reach of current thought, in a frontier where physics itself seemed to unravel. In laboratories and universities, scientists wrestled with the invisible. They built ever more precise models, tested the implications of every candidate explanation, and chased after faint signatures that might betray dark energy's nature. Yet at every turn, they collided with the same unsettling truth: no physical mechanism could be confirmed. The cosmological constant seemed too simple, yet too arbitrary, offering no hint of why its value was so small compared to quantum expectations. Quintessence fields demanded exotic particles never before seen, elusive entities that might forever escape direct detection. Some invoked modifications to gravity itself, imagining that perhaps Einstein's equations, so majestic in describing stars and black holes, faltered at cosmic scales. Others spoke of hidden dimensions, of strings vibrating in unseen realms, whose harmonies might explain the delicate push of expansion. But for every theory proposed, counter-arguments rose swiftly. Observations of the cosmic microwave background, of galaxy clustering, of gravitational lensing, each added constraints, narrowing the possibilities, yet never revealing the truth. The struggle was not merely scientific but philosophical, for there was a force shaping the entire universe, and yet it slipped through every net of human reason. It was as though nature had written her greatest secret in a language just beyond comprehension, allowing a glimpse but never the full revelation. The pursuit was relentless, but it was also humbling, a reminder that humanity, even armed with satellites, telescopes, and mathematics, still stood as an infant before the immensity of the unknown. From the void of uncertainty rose new cosmological models, daring attempts to weave dark energy into the tapestry of the universe. Some proposed that it was not constant at all, but dynamic, a shifting field whose influence waxed and waned across epochs. Others speculated about interactions between dark energy and dark matter, a hidden dialogue in the shadows that shaped the growth of galaxies and the fate of cosmic structure. Still others imagined that dark energy might decay in the future, leading not to a big rip, but to a gentler slowing, or even a reversal into collapse. These models populated conferences, papers, and late-night discussions, each carrying not only mathematics, but stories of possibility. The universe, once imagined as simple and inevitable, became a stage for countless potential destinies, each dependent on the elusive nature of this unseen force. Observational missions were designed with these models in mind: surveys of supernovae, maps of cosmic microwave background, anisotropies, measurements of baryon acoustic oscillations. Each dataset became a piece of a puzzle whose full picture remained stubbornly incomplete. These models did not yet deliver answers, but they stretched imagination, forcing scientists to see the cosmos not as static truth but as unfolding mystery. For, in every proposal lay the acknowledgement that the universe was stranger than any single framework, a reminder that even in the age of precision cosmology, mystery remained the most faithful companion of science. The discovery had landed like a tremor in the bedrock of modern science, and the first instinct was to doubt its very existence. When astronomers initially found that Type Ia supernova seemed dimmer than expected, the natural conclusion was not that the cosmos itself was accelerating, but that some error must lurk in the shadows of measurement. Teams across the globe combed through their observations, scrutinizing every calibration of the telescopes, every correction for dust that might dim a star's light, every statistical method that turned faint photons into cosmic distances. Months turned into years of rechecking, yet the results stubbornly remained. The universe was not simply expanding. Its expansion was quickening, as if some unseen pressure were prying the galaxies farther apart. In the controlled language of science, it was called cosmic acceleration. In the hushed conversations of hallways and conferences, it was something stranger, something terrifying. The thought lingered. What if human understanding had reached a wall of reality that could not be scaled by ordinary means? Such doubt was not denial, it was rigor, the methodical skepticism that guards science against illusion. But the deeper they looked, the clearer the signal became. It was not an error. It was a message written across the stars, one that humanity had only just learned to read. The next step was to hold this fragile discovery against an entirely different backdrop, the faint afterglow of the Big Bang itself. The cosmic microwave background, a wash of ancient light still bathing the universe, carried within it the fingerprint of early expansion. By mapping its subtle temperature fluctuations, cosmologists could reconstruct the geometry of space on the largest scales. Satellite missions like COBE, WMAP, and later Planck charted this relic radiation with exquisite detail, producing maps that were both beautiful and unsettling. When compared with the supernova evidence, the alignment was striking. Both whispered the same truth. The universe was dominated not by visible matter, not by dark matter alone, but by an even greater, unknown, invisible energy that filled the void. This cross-verification between explosions of dying stars and the gentle hiss of primordial light was more than coincidence. It was convergence, the kind that forces theory to bend under the weight of observation. Too many, it was the moment when disbelief began to yield to reluctant wonder. The fabric of reality was not only more expansive than imagined, it was ruled by a force no one could yet define. This realization was less a conclusion than an opening, a doorway into questions as vast as the cosmos itself. With doubt eroded, astronomers turned to larger scales, seeking confirmation in the grand architecture of the universe. Massive galaxy surveys, mapping millions of cosmic islands across billions of light years, became the next instruments of truth. Projects like the Sloan Digital Sky Survey swept the sky systematically, capturing the distribution of galaxies like points in an immense three-dimensional lattice. Their clustering, their spacing, their subtle patterns of expansion all spoke the same language: acceleration. The farther the gaze stretched, the stronger the case became. Galaxies were not merely drifting outward. Their recession was quickening, as if the universe were an ocean and some unseen tide was pulling it apart with mounting force. What had begun with the faint light of a handful of supernovae was now echoed by the architecture of the cosmos itself. Each layer of evidence, supernova, microwave background, galaxy clustering, wove into a single tapestry of inevitability. The conclusion could no longer be brushed aside. Something unseen, unmeasurable, yet undeniable was at work. And though it was named with clinical simplicity as dark energy, the words only masked the depth of the enigma. It was the largest component of the universe's composition, yet the least understood. The cosmos was whispering a secret, and humanity had barely begun to listen. In an effort to bring order to chaos, cosmologists introduced a new parameter, a measure of this mysterious force's share in the cosmic ledger. It was called omega lambda, dark energy density parameter. In the neat equations of cosmology, it represented the fraction of the universe governed by this invisible expansion. Matter, both ordinary and dark, made up less than a third. Radiation, once dominant in the early fireball, was reduced to near insignificance. The rest, nearly 70%, was omega lambda. With a symbol and a number, the greatest mystery of modern science was given a place in the equations. Yet the precision of the mathematics did not lessen the mystery. If anything, it deepened it. How could something so abstract, so beyond the reach of direct detection, dominate the fate of the universe? It was like naming a ghost, assigning it a share of reality without understanding its essence. The equations balanced, the models worked, but the meaning remained absent. In that absence grew a quiet unease, for physics had always striven to tie numbers to mechanisms, theory to cause. Here was an exception, a placeholder for ignorance, enshrined at the heart of cosmology. The omega lambda parameter was not an answer, but a confession, one written in the language of science itself. Yet naming alone did not settle the debate. For behind the numbers lay a choice. Was dark energy a static, unchanging feature of space-time, the resurrection of Einstein's discarded cosmological constantor? Was it dynamic, evolving, something closer to a field that shifted with time? The first interpretation offered simplicity, a constant vacuum energy pressing outward, forever the same. The second, more exotic, envisioned a fluid-like essence, dubbed quintessence, whose strength might wax and wane as the universe aged. Both fit the observations, at least in the early days, but each carried vastly different implications. If a constant, the universe's acceleration would continue endlessly, stretching galaxies apart until only emptiness remained. If dynamic, the future was uncertain, it might slow, reverse, or even tear space-time in a final, catastrophic event. The debate was not merely technical, it was philosophical, a question of destiny hidden within equations. To decide between them required more than imagination. It required new eyes, sharper tools, instruments capable of seeing not just galaxies but the invisible currents between them. Thus began a new era in observational astronomy, a race to build observatories designed not for the light of stars but for the faint imprints of a force that revealed itself only indirectly. Humanity was assembling a new lens through which to view the cosmos, one not made of glass, but of persistence and audacity. The 21st century became the age of dedicated quests to probe dark energy. Telescopes and satellites were conceived with a singular purpose: to measure the expansion history of the universe with unmatched precision. The Dark Energy Survey, scanning hundreds of millions of galaxies, traced cosmic structures across billions of years. The upcoming Euclid mission, launched by the European Space Agency and NASA's Roman Space Telescope, were designed to map the geometry of the cosmos with a sensitivity once unimaginable. These instruments would not detect dark energy directly, for it neither emits nor absorbs light. but they would map its fingerprints, the stretching of galaxy clusters, the bending of light through gravitational lensing, the statistical patterns written into the distribution of matter. Each dataset was another thread, weaving the silhouette of the unseen. The challenge was profound, to observe that which refused to be observed. Yet through patience and ingenuity, the faint outline of this mysterious force grew sharper. It was a pursuit as much philosophical as scientific, for every step closer revealed not clarity but deeper strangeness. The universe seemed determined to show its shape, but not its soul. Still, at the heart of the effort lay a deeper unease. How could Einstein's general relativity, a theory that had explained gravity for over a century with perfect elegance, coexist with this invisible, repulsive force? Relativity described space-time as a pliable fabric, curved by mass and energy. But dark energy acted not like mass, not like matter, but as something woven into the very vacuum. It was as though the equations of gravity had a hidden term, an echo of Einstein's abandoned constant that now re-emerged with haunting relevance. Physicists wrestled with the possibility that general relativity itself might be incomplete, that beyond its beauty lay a hidden flaw. Some models sought to extend Einstein's framework, modifying gravity to account for cosmic acceleration. Others posited extra dimensions, invisible yet influential, whose presence could mimic the effect of dark energy. Each attempt was bold, and each raised more questions than it answered. The suspicion grew that perhaps dark energy was not a thing at all, but a signpost pointing to new physics, as yet unimagined. The pursuit of dark energy became not just a search for an unknown substance, but a challenge to the very foundation of understanding. The more humanity measured, the clearer the paradox became. Dark energy was not an anomaly at the margins. It was the dominant feature of the cosmos. More than matter, more than light, it defined the universe's fate. The haunting realization settled across the scientific world. Most of existence was not made of the atoms that formed stars, planets, and people. It was made of something unseen, unmeasured, and unnamed in any language of human experience. The night sky, once thought to be filled with endless galaxies, now appeared as a fragile residue, the visible remnant of a universe ruled by the invisible. It was a reversal of perspective as profound as any in history. Just as Copernicus had displaced Earth from the center, and Einstein had bent time with relativity, so too did dark energy erase the comfort of the visible. Humanity was not built of the universe's essence, but of its leftovers. The great silence of the cosmos was not emptiness, but fullness of another kind, one that science could not yet touch. In this silence lingered a question both terrifying and beautiful. What does it mean to live in a universe where the most powerful force is the one least understood? Under the weight of growing evidence, cosmologists turned to the silent glow of the cosmic microwave background, the afterglow of the Big Bang itself, as if consulting the universe's own autobiography. Launched in 1989, NASA's COBE satellite had already mapped this faint radiation, and in 2001, its successor, the Wilkinson Microwave Anisotropy Probe WMA, purified the image. Patterns in this ancient light acted as cosmic fingerprints, encoding information about the composition, age, and curvature of the universe. What they revealed harmonized with the unsettling supernova data, an unseen component contributing roughly 70% of the universe's energy budget was shaping the cosmos. Years later, the Planck mission sharpened this view, confirming that the fingerprints of dark energy were etched into the earliest moments of time itself. The acceleration was not a trick of miscalibrated telescopes or flawed analysis. It was inscribed in the very structure of the universe. Scientists who had once doubted were forced into reluctant awe. The cosmos itself was confessing, in whispers across billions of years, that it was not governed by visible matter alone. The cosmic microwave background became a lantern in the darkness, and with it came both revelation and dread. Dark energy was not a fleeting miscalculation, but a permanent feature of reality. The faint hiss of radiation from the birth of time was now speaking of a future none could yet fully imagine. And as each pixel of data resolved into clarity, the realization deepened that humanity was standing before a mystery older and grander than any mythology had ever dared to dream. Large-scale galaxy surveys soon took up the role of arbiters, tracing the scaffolding of the cosmos across billions of light-years. Telescopes mapped the clustering of galaxies, like cities strung along invisible highways of dark matter, their distribution betraying the hand of an unknown force stretching space itself. Projects like the Sloan Digital Sky Survey charted the positions of millions of galaxies, revealing a grand cosmic web whose filaments and voids told a story of growth interrupted. Instead of slowing under the pull of gravity, the web seemed to be loosening, as though the threads themselves were being pulled taut by some hidden current. Baryon acoustic oscillations, the frozen ripples from sound waves in the early universe, acted as a cosmic ruler, allowing astronomers to measure expansion with exquisite precision. These surveys confirmed, again and again, that the expansion was not only real but accelerating. Each independent method, supernova, microwave background, galaxy clustering, converged upon the same conclusion. The result was unsettling in its unanimity. No escape remained in the possibility of error. The universe was governed by a force no one could see, a presence that neither absorbed nor emitted light, yet dictated the fate of galaxies. For the scientific community, the convergence of data eliminated doubt but amplified confusion. To measure so clearly what could not be explained was to glimpse the edge of knowledge itself, and beyond it, a darkness as infinite as the sky. The cosmos was speaking in numbers, and the numbers spoke of an enigma without precedent: the launch of the Wilkinson microwave anisotropy probe in 2001 marked a new turning point in the quest to understand the unseen. For years, the faint afterglow of the Big Bang microwave radiation, stretched thin across the heavens, had been studied, but never with such sensitivity. WMAP peered into that light, capturing the ancient ripples imprinted when the cosmos was only 380,000 years old. These ripples carried the fingerprints of matter, radiation, and something more elusive, an unknown component shaping the universe's destiny. The data revealed, with startling precision, that the cosmos was not merely expanding but accelerating, and that some vast unseen energy was responsible. In the cold geometry of its maps, scientists found a universe composed not mostly of stars, galaxies, or even dark matter, but of a force unlike anything imagined: dark energy. Rough calculations transformed into chilling certainties. Nearly 70% of all existence was attributed to this mysterious phenomenon. The numbers carried weight beyond their abstraction. They spoke of a cosmos dominated not by what was seen, but by a silence pressing outward across every horizon. WMAP's measurements etched into science the uncomfortable truth that the universe was ruled by something without name, without origin, and without comprehension. The invisible had become undeniable, and the quest to know it had only just begun. If, while Map had opened the door, the Planck satellites stepped inside. Launched in 2009. It was designed to see the microwave background with greater clarity than any instrument before it. Over 4 years, Planck gathered light from the ancient sky, each photon a traveler since the dawn of time. Its data refined the picture WMAP had drawn, offering an almost surgical map of the early universe. From these patterns, cosmologists extracted exquisite detail, the exact proportion of matter, and dark energy, the curvature of space, the age of the universe to within less than 1%. Planck confirmed what WMAP had suggested, that dark energy was not a statistical fluke, but an embedded truth. About 68.3% of the universe was found to be composed of this force, while ordinary matter, the stars, planets, and people, mounted to less than 5%. The rest, dark matter, made up the remainder. Such precision was both triumph and torment. The numbers were crisp, unyielding, and yet they provided no mechanism, no explanation of what dark energy truly was. The Planck satellite gave humanity an accounting of the cosmos down to fractions of 1%, but left its greatest mystery untouched. The deeper the view, the clearer the ignorance became, and the more haunting the silence behind the acceleration grew. Baryon acoustic oscillations became the next great milestone in the pursuit of the unseen. Long before galaxies had formed, when the cosmos was still a hot, dense plasma, pressure waves rippled outward through the young universe. These waves sound in the medium of primordial matter, and radiation froze in place when the universe cooled, leaving behind a faint but measurable imprint in the large-scale distribution of galaxies. Billions of years later, astronomers began to detect this cosmic rhythm, this faint memory of ancient vibrations, by mapping the clustering of galaxies across vast regions of space. They uncovered a ruler etched into the universe itself, a pattern stretching hundreds of millions of light-years. This ruler allowed scientists to measure the expansion history of the cosmos with uncanny precision, confirming again that something invisible was driving galaxies apart faster and faster. The frozen echoes of ancient sound waves, now called baryon acoustic oscillations, gave independent proof that dark energy was real, woven into the very fabric of cosmic structure. Each survey, Sloan Digital Sky Survey, BOSS, and beyond, traced ever more detailed maps of these primordial ripples, and each confirmed the same unsettling conclusion. Acceleration was not an illusion of light or miscalculation, but an immutable truth written into the scaffolding of the cosmos. The universe's heartbeat had been measured, and its rhythm whispered of a future that grew only more mysterious with every confirmation. Another line of evidence emerged from the strange distortions of light itself. Gravitational lensing. Prediction that mass bends space and warps the path of light became an unexpected ally in tracking the fingerprints of dark energy. Distant galaxies appeared stretched, smeared, or magnified by the invisible weight of matter lying between them. And Earth, by studying millions of such distortions, astronomers traced not only the presence of dark matter, but also the subtle tug of dark energy. The cosmic web, that grand lattice of galaxies spanning the universe, seemed thinner, more stretched than gravity alone could explain. It was as though dark energy were pulling gently at the scaffolding of creation, softening its structure over billions of years. Weak lensing surveys, such as the Canada-Francois Telescope Legacy Survey and later the Dark Energy Survey, mapped these delicate shears in light with unprecedented detail. They showed how structures grew more slowly than expected, how voids expanded more rapidly, how the balance of attraction and repulsion was shifting under an unseen hand. Through the bending of light, the universe revealed not only its matter, but its defiance of matter. Dark energy left no glow, no shadow, yet its presence was etched in every warped galaxy and every faint arc of light crossing the cosmos. As these observations accumulated, a new picture of reality came into focus. Ordinary matter, the familiar atoms that build stars, planets, oceans, and life, was relegated to a cosmic minority. Dark matter, unseen yet gravitating, comprised more, but the dominant component, the true sovereign of the cosmos, was dark energy, commanding nearly 70% of all existence. This number was more than a statistic. It was an existential revelation. For the first time, humanity realized that the majority of reality was composed of something neither seen nor understood. Cosmology, once the study of luminous galaxies, became the study of absence, of force without form. The Copernican revolution had displaced Earth from the center. Relativity had reshaped the notions of time and space. Now, dark energy placed all of existence in shadow, revealing a universe where ignorance outweighed knowledge by an unfathomable measure. The standard model of cosmology, the CDM model, was reshaped around this presence, embedding a cosmological constant or its alternatives into the equations of cosmic evolution. It was a triumph of precision science, but also a recognition of profound incompleteness. The known universe was only a fraction of the whole, and the rest was a mystery that defied comprehension. From these foundations, scientists dared to ask what the future might hold. With the strength of dark energy measured, rough sketches of cosmic destiny were drawn. If this repulsive energy remained constant, galaxies not bound by gravity would drift endlessly apart. Over unimaginable timescales, stars would fade, galaxies would empty, and the universe would settle into cold darkness, fate called heat death. But if dark energy's strength grew over time, an even more violent end loomed. Galaxies, solar systems, planets, and finally atoms themselves could be torn asunder in what theorists named the Big Rip. Some speculated, instead, on a reversal, that dark energy might decay or transform, allowing gravity once more to dominate, bringing about a collapse into a final singularity. Each possibility was consistent with observation, and yet none could be confirmed. The cosmos appeared to offer multiple fates, all dependent on the behavior of an energy never seen, never touched, and never explained. To gaze into the future of the universe was to stare into the opacity of dark energy, a horizon where knowledge thinned into speculation. The more data sharpened the numbers, the more abstract and incomprehensible the reality became. In time, the questions surrounding dark energy grew sharper, not softer. The Planck satellite, successor to WMAP, delivered maps of the cosmic microwave background with a fidelity almost unimaginable. It revealed the geometry of the universe to be flat within a margin of error thinner than a hair's breadth. An observation consistent only if dark energy filled space with uncanny uniformity. The fingerprints of this force were undeniable. Slight variations in temperature across the early cosmos matched perfectly with the later distribution of galaxies, stars, and voids. And yet, while the numbers grew ever more precise, the essence remained beyond reach. It was as if the universe had given humanity its measurements but withheld its meaning, allowing calculations but refusing comprehension. The era of precision. Cosmology had begun, but with it came the unsettling realization that exactness could still conceal truth. A puzzle can be measured to perfection and still remain unsolved. The CDM model called dark matter plus a cosmological constant became the reigning framework. The equation that described the evolution of the cosmos from its birth to its projected future. It was elegant, simple, and devastating. Dark matter held the galaxies together. Dark energy pushed them apart. Between them, they accounted for 95% of all that exists, leaving ordinary matter, the atoms of planets and people, reduced to a cosmic afterthought. This was the standard model of cosmology, the best description of the universe ever achieved, and yet, in its very success, lay the shadow of ignorance. For neither dark matter nor dark energy had ever been directly detected. Their existence was inferred only by the absence of alternatives. Humanity, for all its instruments and ingenuity, was left orbiting an abyss of unknowns. Gravitational lensing deepened the mystery. As surveys grew larger and telescopes more powerful, astronomers traced the delicate shears in starlight across millions of galaxies. The cosmic web revealed its structure in ghostly detail, its filaments and voids etched into the darkness. But the patterns spoke of something unnatural. Structures were growing slower than gravity alone would predict, as though an invisible hand was pulling gently outward, preventing galaxies from gathering as tightly as they should. These measurements whispered the same refrain sung by supernova and by ancient light. Expansion was not only real, but accelerating. It was a chorus of evidence, yet a silence of understanding. At the heart of these observations lurked the most haunting realization of all. The universe, in its grand totality, was not what it appeared to be. Stars, nebulae, galaxies, the luminous scaffolding of existence were only fragments of the whole. The vast majority of reality, the true substance of the cosmos, was something unseen, untouchable, perhaps unknowable. Dark energy had become the dominant feature of the universe, not by its presence, but by its absence. It was the emptiness that defined everything else. The cosmos had turned from a theater of light into a shadow play of mysteries. Humanity's gaze, once fixed on galaxies and stars, now fell into the invisible spaces between, searching for meaning in the void. The measurements were unrelenting. Each new telescope, each refined dataset, pointed toward the same haunting truth. Dark energy was not only real, but its value seemed exquisitely, unnervingly precise. The strength of this invisible force was so finely balanced that it had only recently overtaken gravity in its cosmic tug-of-war. A little weaker, and galaxies would have collapsed into themselves long ago. A little stronger, and stars might never have formed at all. It is this delicate knife-edge balance that haunts cosmologists. Why this number, and why now? Among the infinite possibilities for a cosmic expansion rate, why should the universe select one that allows life to emerge, only to confront its mystery in the very era when intelligence arises to measure it? This strange convergence is known as the coincidence problem, and it casts a shadow of unease across the field. The timing feels too precise, as though the cosmos had arranged itself for human observation, though science resists such anthropocentric conclusions. Still, the silence lingers, unanswered, unsettling. Theories multiplied, each more daring than the last. Some physicists proposed phantom energy, a form of dark energy even stranger than the cosmological constant. Unlike the steady push of a vacuum, phantom energy, would grow stronger with time, accelerating the universe at an ever-increasing rate. In such a model, expansion would not simply continue, it would spiral into violence. The very fabric of space would stretch with growing fury, pulling galaxies apart unraveling clusters, then stars, then planets, then molecules, until even atoms themselves could no longer hold together. It is a scenario known as the Big Rip, a universe undone not in a sudden collapse, but in a slow, unstoppable tearing, where every bond in nature is eventually broken. The timeline depends on the true strength of dark energy, perhaps tens of billions of years, perhaps sooner, but the implication is clear. No structure, no matter how fundamental, would survive. For others, the universe's fate might be more subdued, though no less chilling. If dark energy remains constant, the cosmos will expand forever, galaxies receding beyond sight until the night sky empties into blackness. Over unimaginable stretches of time, stars will exhaust their fuel, black holes will evaporate, and matter itself may decay into nothingness. This is the slow march toward heat death, a future without heat, light, or structure, only an endless expanse of cold silence. Whether the cosmos ends in violent disintegration or in quiet dissolution, the outcome is the same. The familiar universe of stars and galaxies is temporary. The question is not whether it ends, but how. These scenarios force reflection on deeper questions. Why should humanity exist at this fragile juncture, when dark energy has just emerged as the dominant force in the cosmos? The anthropic principle offers one possible answer, perhaps countless. Universes exist, each with different laws, and only in this one are the conditions right for life to arise and wonder about its fate. In such a view, existence itself is an accident of cosmic lottery, and the universe is not tuned for humanity, is humanity that arises in the rare universe capable of permitting life. This principle is controversial, straddling the line between science and philosophy, but it looms in the background, a whisper of meaning in the silence of numbers. What is certain is that the future is not ours to control. No technology, no escape, no strategy could resist the pull of expansion. Even light itself, the fastest messenger in nature, cannot outrun the stretching of space. In the far future, civilizations, if they endure, will see their skies darken, as neighboring galaxies slip forever beyond the cosmic horizon. The universe will grow lonelier, colder, and more fragmented with each passing epoch. Whether it ends in a shattering rip or in a gentle fade, the silence of fate will close over everything. Astronomers speak of dark energy as a storm sweeping across eternity, an invisible tempest whose winds cannot be felt, but whose effects shape the destiny of all things. Unlike earthly storms, this one cannot be outrun, cannot be predicted with certainty, and cannot be survived. It is vast, unstoppable, and utterly indifferent. Humanity, in its brief moment beneath the stars, can only look upward, measure its traces, and wonder at the paradox. The greatest storm of all time is one no eye can see, and no voice will remain to tell of its passing. The measurements revealed something almost unnerving. Dark energy's strength, its cosmic value, was not random chaos, but a number of exquisite precision. If it had been ever so slightly weaker, gravity would have triumphed. Galaxies would have collapsed long before stars and planets had time to emerge. If it had been stronger, space would have torn itself apart in the early universe, scattering atoms before they could gather into suns. Yet here, at this fragile balance point, it is just strong enough to accelerate expansion, but just late enough to allow worlds and life to appear. This is the essence of the coincidence problem. The question of why the universe has chosen this value at this time. It is as if the cosmos has revealed its deepest card only when intelligent eyes have evolved to see it. A coincidence, or a deeper truth? Science resists the temptation of destiny, but the silence of numbers unsettles even the most cautious minds. This coincidence appears not only in the numbers, but in the timing. For billions of years, matter and radiation controlled the cosmos, while dark energy remained hidden, its influence negligible. Only in the present epoch only now does it become dominant, accelerating the expansion just as humanity learns. To measure it, the parallel is haunting. To many cosmologists, it feels like standing at the crest of a hill, realizing the slope beneath one's feet has already shifted. A force beyond comprehension has begun to dictate the shape of everything, and humanity arrives in time to watch the first shadows of its influence. Coincidence or something profound? The question lingers unanswered, an echo beneath the dome of stars. Theorists searched for explanations. Some clung to the idea of a true cosmological constanta, steady vacuum energy pervading all space, unchanging, eternal. Others dared to imagine more unstable forms, fields that shift and strengthen with time. Among these, the most unsettling was phantom energy. Unlike the calm, steady hand of the constant, phantom energy does not merely persist, it grows. Its power increases with every tick of the cosmic clock, driving the expansion faster and faster. And in such a universe, the future is not merely one of loneliness, but of destruction. The expansion does not approach a steady state. Toward catastrophe, in the Big Rip scenario, the expansion intensifies until no structure can survive. First, galaxy clusters dissolve, torn apart by the accelerating space between them. Then galaxies themselves are ripped open, stars no longer held in orbit. Planets drift away from their suns. But the expansion does not stop. Molecular bonds fail, atoms unravel, and even the fundamental particles of matter, the quarks and electrons themselves, are torn from existence by the relentless stretching of space-time. It is not an explosion, but an unweaving, the dissolution of all things, in a crescendo of acceleration. To speak of such an end is to speak of the annihilation not only of life and matter, but of the very framework of existence. The timescale of the Big Rip is not immediate, but stretched across cosmic horizons, depending on the measured value of dark energy's equation of state. Such an ending could arrive tens of billions of years from now. For a universe already 13.8 billion years old, that is both unimaginably distant and yet terrifyingly finite. Stars, yet unborn, may never live long enough to shine their full brilliance. Civilizations, far beyond the imagination of today, might flourish, only to vanish in the silent disassembly of reality, and in the deepest scenario, even light itself, the messenger that carries the story of the universe, will find no refuge, undone not by gravity, but by the very expansion of the medium through which it travels. This is the vision that phantom energy paints, a cosmos that does not end with the slow cooling embers of eternity, but with a violent unraveling, as if the fabric of space has decided it can no longer bear the weight of existence. Yet not all models are so catastrophic. Some argue that dark energy may be stable, eternal, locked as a cosmological constant. In such a universe, galaxies would drift apart endlessly, isolation deepening until each cosmic island lives in solitude. Surrounded by darkness, the rest of the universe receding beyond any possible signal or voyage. Stars would exhaust their fuel, white dwarfs and black dwarfs replacing the fire of creation. Even black holes, engines of gravity, would eventually evaporate through Hawking radiation. leaving behind only a whisper of energy in an ever-expanding sea of nothingness. This is the so-called heat death, an eternal equilibrium where nothing new can ever happen, where the universe becomes a featureless expanse. Compared to the violence of the Big Rip, it is a quieter ending, but no less final. In both scenarios, the arrow of time points only one way, toward dissolution. Cosmologists debate these fates with equations, yet every answer leads back to the same haunting truth. Dark energy holds the key, and dark energy itself remains unknowable to measure. It is to watch shadows move without ever glimpsing the hand that casts them. Observers map galaxies, trace supernovae, measure the temperature fluctuations of the cosmic microwave background, but the essence itself escapes. It does not shine, it does not absorb, it does not bend to the instruments crafted by human ingenuity. It exists only as an influence, as an effect, as the silent sculptor of destiny. This absence makes its presence even more formidable. For what is more unsettling than a force that rules everything, yet refuses to be seen? The anthropic principle emerges in whispers, a suggestion born of desperation. Perhaps the universe is not tuned for observers, but observers exist only in those rare universes that permit them. If there are countless universes, each with different laws and constants, then only in one such as this could galaxies form. Could chemistry take root? Could consciousness arise to ask why? And so the question of coincidence might not be coincidence at all, but inevitability within a larger, unseen multiverse. Yet such speculation hovers at the edge of science, tethered more by philosophy than by data, and still the mystery deepens. The known universe rests upon two towering pillars of understanding: quantum field theory, which rules the infinitesimal dance of particles and forces, and general relativity, which governs the grand curvature of space-time itself. Both have proven almost impossibly precise, each confirmed to more decimal places than any human invention should ever have demanded. And yet, when asked to coexist, they clash like fire and ice. Dark energy, with its strange pressure and unyielding acceleration, intensifies this rift. It appears in Einstein's equations as a cosmological constantan extra term, a kind of cosmic afterthought. But when physicists calculate what quantum field theory predicts for the vacuum energy of empty space, the result overshoots observation by an absurd factor, not by twice, not by 1,000, but by 10 to the power of 120. This is not a small mistake. It is the largest known discrepancy between theory and reality in all of science. The mystery deepens further when the observed value of dark energy is examined. It is not zero, as might have been hoped, and not overwhelmingly large, as theory insists. Instead, it rests at a delicate, improbable number so small it allows galaxies to form, yet so large it dictates the universe's ultimate fate. Why this number? Why now? Too many physicists, it seems not just a puzzle, but a cosmic provocation, as if the universe were pointing toward a truth still beyond reach. Some turn to string theory, the most ambitious attempt to unify all known forces into a single framework. In this strange mathematics, particles are not points, but vibrating strings, each frequency giving rise to mass, charge, and spin. Within this vision lies a landscape of possibilities, countless vacuum states, each with different values for the fundamental constants of nature. Among these possibilities, some universes would collapse instantly, others would expand too violently to allow structure. But a rare few, scattered across the vast landscape, might host stars, planets, and perhaps life. In this way, the observed value of dark energy could be understood not as unique, but as one roll of the cosmic dice, chosen from an almost infinite array. This line of thought gives rise to the idea of a multiverse, an unseeable ocean in which our universe is but a single wave. In such a framework, the strange fine-tuning of dark energy ceases to be miraculous. It is, instead, a consequence of selection. Only in a universe where dark energy rests in this improbable balance could galaxies form and beings evolve to contemplate its meaning. All other universes remain silent, empty, sterile. Yet the multiverse, while mathematically rich, remains observationally barren. There is no telescope that can pierce beyond our cosmic horizon to verify its truth. It lingers at the edge of science, half physics, half philosophy, suspended between bold imagination and the need for proof. In the search for cosmic truth, there is one explanation that towers above all others in both simplicity and elegance. It is the cosmological constant, known by the Greek symbol lambda, reintroduced into the language of physics after a long exile. Once Einstein himself had written it into his equations to maintain a static universe, a term designed to counterbalance gravity and hold the cosmos steady. When expansion was discovered, he called it his greatest blunder, believing the constant had no place in reality. Yet decades later, as evidence mounted that the universe was not only expanding but accelerating, P returned from obscurity, not as a mistake, but as the leading explanation for the strange, repulsive force now called dark energy. The cosmological constant describes dark energy as an intrinsic property of space itself, unchanging, uniform, eternal. In this view, every cubic centimeter of the universe carries within it a small but unrelenting pressure, a hidden energy of the vacuum that cannot be removed. It does not thin as the cosmos expands, nor fade as stars burn out. It is woven into the very fabric of existence. Though invisible, it shapes the trajectory of all things, dictating the fate of galaxies, clusters, and the universe itself. Evidence for this model, known as CDMD, lambda-cold dark matter paradigm, emerged from multiple directions. Observations of distant supernova in the late 1990s revealed that galaxies were receding faster than expected, their light stretched by an accelerating expansion. Measurements of the cosmic microwave background, the faint afterglow of the Big Bang, showed a universe geometrically flat, requiring a hidden energy component to make the numbers balance. Baryon acoustic oscillations, subtle ripples imprinted on the distribution of galaxies, added yet another confirmation. Together, these anchors painted a consistent picture. The simplest model, with a cosmological constant at its heart, fits the data with remarkable precision. Yet within this elegance lies unease. The value of lambda is almost impossibly small compared to what quantum physics predicts. By rights, the vacuum energy of space should be staggeringly large, curled up into a seething maelstrom of particles and fields. Instead, it is measured at a whisper, a number so minuscule that it allows stars, planets, and life to exist. Why this number? Why not zero? Why not infinite? No one knows. Still, the cosmological constant holds its ground. Most scientists, when pressed, cautiously lean toward it, not because it is satisfying, but because it works. It explains the acceleration. It fits the observations. And unlike more exotic alternatives, it requires no extra moving parts, no speculative new fields or hidden dimensions. It is not a complete answer, but it is a foundation, a baseline against which all other theories are measured. If lambda is indeed the true description of dark energy, then the future unfolds with a chilling inevitability. Expansion will never end and never slow. Galaxies will drift apart until only a handful remain visible to any observer. Stars will burn out, one by one, leaving behind a cosmos that grows colder, emptier, and lonelier with each passing eon. The final destiny will not be fire, but silence. In the shadowed corridors of cosmology, beyond the orderly realm of mainstream models, lies a territory of speculation. Here, the imagination of science stretches outward, weaving daring visions of what dark energy might be. These are theories born not from reckless fantasy, but from the acknowledgement that the simplest answered the cosmological constant may only be part of the story. They are fragile, uncertain, and sometimes extreme. Yet they attempt to capture the hidden pulse of the cosmos in forms unimagined by ordinary physics. Among the most prominent of these is quintessence, a name that echoes the ancient philosophers' search for a fifth element beyond earth, air, fire, and water. In modern science, it takes the form of a rolling scalar field, an invisible energy that permeates space, dynamic rather than static, shifting its strength with the evolution of time itself. Unlike the cosmological constant, quintessence is not frozen, but alive, waxing and waning as the universe grows. The mathematics of quintessence suggests that its energy density could change as the cosmos ages, subtly altering the pace of acceleration. If true, then the distant past may not mirror the present, and the far future may not echo today. This idea, if confirmed, would mean dark energy is not a permanent background, but a cosmic actor, evolving alongside galaxies, stars, and life. Observational programs, such as the Dark Energy Survey and the upcoming Euclid mission, scan the distribution of galaxies with exquisite detail, hoping to detect the fingerprints of this changing force. If they succeed, they may reveal that the acceleration of the universe is not a constant whisper but a shifting rhythm, as if the cosmos itself were breathing through the rise and fall of an unseen field. Yet even more dramatic possibilities lurk at the edges of speculation. Phantom energy, an extreme cousin of quintessence, predicts a universe not destined for silence but for rupture. If dark energy grows stronger with time, overpowering all other forces, it could unravel the very scaffolding of the cosmos. Galaxies would be torn apart, stars shredded, planets ripped from their orbits. In the final moments, even atoms and subatomic particles would be pulled asunder, leaving nothing but a gaping void. This apocalyptic fate is known as the Big Rip. Its timescale is uncertain, perhaps hundreds of billions of years away. Perhaps closer, but its logic is chilling. If phantom energy exists, the universe carries within it the seed of its own annihilation. An unstoppable crescendo that ends not in fading light, but in catastrophic dismemberment. Such visions may seem fantastical, yet they arise naturally when physicists stretch the equations of general relativity and quantum theory into unexplored regions. Each hypothesis is a mirror held up to ignorance, reflecting not certainty but possibility. Whether quintessence, phantom energy, or something stranger still, the speculative theories of dark energy reveal the lengths to which science must travel when confronted with a mystery that resists all ordinary explanation. Beyond phantom horizons, other speculative ideas attempt to tie dark energy not to new particles or fields, but to the very structure of reality itself. One of the boldest proposals is holographic dark energy. This vision emerges from the holographic principle, a radical concept born in black hole physics. According to this principle, all the information contained in a three-dimensional volume of space can be described by data imprinted on its two-dimensional boundary. Reality, in this picture, is less like a solid block of matter and more like a hologram, where depth and form emerge from encoded surfaces. If such a principle applies to the universe as a whole, then dark energy may not be a fundamental fluid or field at all. Instead, it may be the expression of the finite information capacity of spacetime itself, the amount of vacuum energy in this view is constrained by the entropy limits of the cosmic horizon. This speculative link between information and energy suggests a profound connection between gravity, quantum mechanics, and thermodynamics. It hints that dark energy could be telling us something about the ultimate bookkeeping of reality, the ledger that balances matter, energy, and information across the expanding fabric of space. In this picture, the acceleration of the universe is not a random accident, but a reflection of cosmic accounting, a natural consequence of how much information the universe can store. Yet such ideas remain deeply abstract, grounded in mathematical beauty more than empirical certainty. Observations of cosmic microwave background fluctuations, large-scale structures, and galaxy surveys may someday test the fingerprints of holographic models, but for now they remain tantalizing whispers at the edge of verifiability. Equally daring is the idea that dark energy may arise from extra dimensions. String theory, with its elegant but elusive mathematics, predicts the existence of hidden spatial dimensions curled beyond the reach of direct detection. In some scenarios, gravity itself may leak into these higher realms, its strength diluted. As it spreads across unseen landscapes, what we perceive as cosmic acceleration could be the shadow of this leakage, distortion created when gravity escapes into dimensions beyond the familiar three. In this view, dark energy is not a substance but a symptom, the visible trace of a deeper geometry in which our universe is only a thin brain, adrift in a higher dimensional sea. The appeal of such models lies not only in their ability to explain acceleration, but in their unification of cosmic mysteries. If true, they would tie together the deepest puzzles of particle physics and cosmology, binding the small and the large into a single fabric of hidden dimensions. Yet, as with holographic energy, the challenge is measurement. Probing the unseen requires experiments of daunting precision, instruments that can detect faint distortions in cosmic structure or subtle deviations in gravitational laws. Projects like the Vera Rubin Observatory and the Dark Energy Spectroscopic Instrument may eventually glimpse such signatures. Until then, extra dimensions remain a poetic speculation, a reminder that the universe may be wider, stranger, and deeper than the thin slice of reality humanity can perceive. There are those who argue that dark energy may not be a thing at all, not a fluid or a hidden field, but a signal that our understanding of space-time itself is incomplete. In this view, Einstein's equations may be a magnificent approximation, yet not the final word. Modified gravity theories explore this frontier. One approach, known as FR gravity, reshapes the fundamental relation between matter and curvature, altering the cosmic equation that governs expansion. Another framework, originally designed to explain galaxy rotation curves without invoking dark matter, has been stretched and extended to the scale of the cosmos. These models dare to suggest that the universe's acceleration is not driven by an exotic energy, but by a subtle shift in the way gravity itself works at immense distances. Such ideas remain controversial. For general relativity has withstood a century of tests with unbroken triumph. From the orbits of planets to the dance of neutron stars, from gravitational lensing to the ripples of space-time recorded by LIGO, Einstein's theory has proven astonishingly resilient. Yet, at the largest scales, where billions of light stretch the very definition of measurement, the cracks may be too faint to see without new instruments. Modified gravity could mimic the effects of dark energy, hiding behind equations that only diverge from relativity in the most delicate ways. If true, then humanity's quest would not be for an unseen force, but for a refinement of the very laws that describe reality. The universe's acceleration would then become less an addition to the ledger of cosmic components, and more a correction to the grammar of space-time itself. Here the mystery deepens into philosophy. Is it more economical to invent a new energy that permeates the cosmos, or to alter the timeless equations that have guided physics for a century? Each path demands boldness. Each admits both elegance and unease. For if the equations change, so too does humanity's confidence in the permanence of its scientific truths. And if dark energy is real, then the cosmos harbors a substance unlike anything known, a silent architect of fate. Neither choice is free of consequence, and both remind us that the story of physics is far from complete. To test these bold possibilities, astronomers now turn to their newest eyes on the cosmos. The Euclid spacecraft, launched by the European Space Agency, peers across the cosmic tapestry with exquisite sensitivity, mapping billions of galaxies across 10 billion years of time. Its mission is to trace the subtle warping of space caused by dark matter and to measure the growth of cosmic structure clues that may reveal whether acceleration is driven by an energy or a modification of gravity. On Earth, the Vera Rubin Observatory prepares to open its gaze upon the heavens with the legacy survey of space and time, a decade-long cinematic record of the sky. Night after night, it will capture billions of galaxies and the faint flickers of distant supernovae, weaving a dynamic atlas of cosmic history. And the dark energy spectroscopic instrument, already charting the three-dimensional distribution of galaxies, is sculpting the most detailed map of the universe ever attempted together. These observatories form a chorus of witnesses, each listening to the faint song of expansion encoded in redshifts and cosmic flows. They do not measure dark energy directly. No detector on Earth can scoop it from space or confine it within a laboratory chamber. Instead, they seek its fingerprints, the way galaxies clustered, the way light bends, the way time itself accelerates. From these patterns, scientists hope to distinguish between a static cosmological constant, a rolling field of quintessence, a phantom storm, or the subtle deviations of modified gravity. The instruments are humanity's lanterns, carried into the abyss, illuminating paths that mathematics alone cannot decide. Yet with each new glimpse, the mystery seems only to deepen. Observations confirm acceleration with ever more certainty, but they do not yet reveal its source. The data fit the cosmological constant beautifully, yet the theoretical problems with vacuum energy remain unsolved. The models of quintessence offer flexibility, but little evidence favors them. Modified gravity lingers as a haunting alternative, possible but elusive. The universe continues to expand in silence, indifferent to human classification, its fate untroubled by the debates of its observers. In this silence lies both the frustration and the wonder of science, the realization that truth may not bend easily to expectation, and that the cosmos may hold secrets forever beyond the reach of certainty. The coming decades promise either clarity or a deeper enigma. If the instruments converge upon a constant, then humanity must confront the paradox of a universe ruled by a quantity so small that no known physics can explain it. If they detect a hint of change, a whisper of evolution in dark energy, then the door opens to a new field of forces, a dynamism woven into the vacuum itself. And if gravity is found to differ on cosmic scales, then physics must rewrite its foundation, daring to reshape the very equation that Einstein once believed would last forever. The quest to understand dark energy has become one of the most ambitious undertakings in human history. Never before has so much machinery, mathematics, and imagination been focused on a single invisible force that cannot be touched, tasted, or captured. It is everywhere, woven into the very fabric of existence, yet it hides like a whisper between the stars. To reveal it, astronomers and physicists have built instruments that scan the heavens with the patience of centuries compressed into a single night. Their work is not a hunt for planets or stars, nor even for galaxies, but for the unseen geometry of the universe itself, the subtle curvature of space-time, and the faint echo of expansion across billions of years. This effort is not the work of one observatory, nor of one nation, but of humanity as a whole, pooling intellect, technology, and persistence into a symphony of discovery. Among these projects, the Dark Energy Survey stands as one of the first grand attempts to capture the shadow of the unknown. Based in the Chilean Andes, using a camera that can peer into the cosmos with extraordinary breadth, it has mapped more than 300 million galaxies. Each faint smudge of light becomes not only a point on a cosmic chart, but a witness to history. For the light of these galaxies has traveled billions of years to reach Earth, crossing epochs when the universe was younger, denser, and less fragmented. By comparing their distribution, brightness, and distortion under the weight of gravity, the survey reconstructs the invisible scaffolding of the cosmos. The patterns of galaxy clustering reveal how structures have grown under the competing influence of gravity pulling inward and dark energy pushing outward. Already, these maps hint at tensions, subtle differences between the observed growth of cosmic structure and the predictions of the standard model. These tensions are not yet decisive, but they whisper that the story of dark energy may be more complex than the simplest cosmological constant. And so the survey continues, pixel by pixel, charting the universe not as a static stage, but as a dynamic canvas of change. Yet the Dark Energy Survey is only the beginning. As the 21st century unfolds, humanity's ambitions reach further, beyond Earth's atmosphere, into the silence of space. In 2023, the European Space Agency launched Euclid, a spacecraft dedicated entirely to the mystery of cosmic acceleration. Euclid carries a wide-field telescope designed to capture billions of galaxies across more than a third of the sky. Its vision is deep and sharp, able to look back 10 billion years into the past. It will not simply collect images, it will measure. Redshifts trace the large-scale structure of the universe and map the subtle distortions of distant galaxies caused by weak gravitational lensing. From these distortions, scientists will reconstruct the invisible web of dark matter and study how its growth has been slowed or accelerated by dark energy. Euclid's mission is ambitious, not because of what it sees directly, but because of the patterns it reveals in the unseen. It is like listening to the silence between notes in a symphony, hearing structure not in sound but in absence. If successful, Euclid may distinguish between a universe ruled by a constant vacuum energy and one animated by a dynamic, time-varying field. It may reveal whether dark energy is steady, like the rhythm of a clock, or restless, like a tide forever shifting. For now, Euclid's gaze has only begun, but already the anticipation among scientists is palpable, as if the cosmos itself were about to whisper one of its oldest secrets. As Euclid charts the heavens from space, another observatory prepares to transform our vision from the ground. In Chile, where the Atacama Desert stretches under skies of extraordinary clarity, the Vera Rubin Observatory nears completion. Unlike Euclid or Day, Rubin is not designed for a single snapshot of the cosmos, but for an unfolding film, a decade-long legacy survey of space and time. Every night, its immense camera will capture thousands of images, scanning the sky again and again, building not just a static map, but a dynamic chronicle. Over 10 years, it will record the flicker of exploding stars, the drift of galaxies, the gravitational warping of space itself. Among its treasures will be the discovery of countless supernovae, cosmic lighthouses whose brightness and distance reveal the accelerating expansion. By observing them across vast epochs, Rubin will allow scientists to trace whether dark energy's influence has remained constant or shifted with time. If dark energy evolves, Rubin may be the first to notice its subtle changes. Like a geologist detecting the slow rise of mountains across millennia, the observatory will generate tens of petabytes of data, more than any project before it, a deluge so vast that only the most advanced algorithms can hope to pass it. Rubin is not just a telescope, but a time machine, showing the living universe in motion, and in that motion, perhaps, the first hints of what dark energy truly is. The universe, however, demands more than images. Light alone, no matter how ancient, carries only part of the story. To probe deeper, astronomers turn to the rhythm of galaxies themselves, their clustering across cosmic distances, and their shifting redshifts as space expands. The Dark Energy Spectroscopic Instrument, or DESI, represents humanity's most ambitious attempt to capture this rhythm. Installed on the Mail telescope in Arizona, DESI wields 5,000 robotic positioners that can each target a galaxy or quasar in the night sky. In a single exposure, it collects the spectra of thousands of objects, measuring their distances with exquisite precision. Over the course of its mission, DESI aims to chart 40 million galaxies, creating a three-dimensional map of the cosmos, larger than any before it. The goal is simple, yet profound: to track how the expansion rate of the universe has changed over time, and how dark energy has influenced the growth of structure. The patterns encoded in this vast web will allow scientists to test whether dark energy is constant, dynamic, or perhaps even a symptom of new physics. DESI's reach is immense. Its survey stretches back 11 billion years, covering nearly the entire span of cosmic acceleration, like a seismograph listening to the tremors of Earth's crust. DESI listens to the ripples of baryon acoustic oscillations, fossil imprints of primordial sound waves frozen into the distribution of galaxies. These ripples provide a cosmic ruler, a way of measuring distances across unimaginable scales. Each measurement becomes a data point in a timeline of expansion, a clue to the shifting balance between matter, radiation, and the enigmatic force that now dominates the universe. As the data accumulates, the first outlines of dark energy's behavior begin to emerge, not yet definitive, but sharper than before, a silhouette forming out of cosmic fog. Yet even DESI cannot escape the boundaries of light. To test dark energy's reach, scientists have turned to a new messenger: the vibrations of space-time itself. Gravitational waves, first detected in 2015, ripple outward from the collision of massive objects like neutron stars and black holes. Unlike light, they are not absorbed or scattered. They travel unimpeded across the universe, carrying with them the pristine signature of distance and time. These waves offer a new method of cosmological measurement, the so-called standard. Sirens, just as standard candles, like supernovae, reveal distance through their brightness. Standard sirens reveal it through their gravitational signal. When paired with electromagnetic observations, light from the same event, astronomers can measure both the distance to the source and the redshift of the galaxy that hosted it. This dual measurement bypasses many uncertainties of traditional methods, offering a direct probe of cosmic expansion. With enough events, gravitational waves could trace the history of the universe's acceleration in a manner independent of light. They could confirm whether the value of dark energy's equation of state, W, remains fixed at -1, as in a cosmological constant, or drifts toward other values that signal new physics. The vision is still in its infancy. Only a handful of standard siren events have been detected so far, but the promise is immense. As next-generation detectors like LIGO's upgrades, Virgo, Cagra, and the future space-based LISA mission come online, the number of observed mergers will soar into the thousands. Each wave will carry a whisper of expansion, and together they may form a chorus strong enough to reveal whether dark energy is steady or restless, constant or evolving. It is a new way of listening to the cosmos, not through light, but through the tremors of existence itself. The pursuit of dark energy now centers on a single symbol, W, the equation of state parameter. Defined as the ratio of pressure to density for dark energy, W captures its essence in a single number. If dark energy is truly Einstein's cosmological constant, then W equals -1 exactly, immutable across time and space. But if dark energy is something more dynamic like quintessence or another exotic field, then we may deviate from this value, or even change with cosmic time. Detecting such variation is one of the foremost goals of modern cosmology. Surveys like Day, Euclid, Rubin, and DESI all converge on this question, each using different methods, different data, and different epochs of cosmic history. By comparing the growth of structure, the brightness of supernova, the lensing of galaxies, and the ripples of baryon acoustic oscillations, scientists seek to pin W down with unprecedented accuracy. Already, measurements constrain it to be close to -1. But the uncertainties remain wide enough to leave room for possibility. The stakes are immense. A confirmed deviation would signal that dark energy is not a simple vacuum constant, but a dynamic field, perhaps rolling slowly across a cosmic landscape. It would force a rethinking of fundamental physics, opening doors to new theories of matter, energy, and spacetime. Conversely, if W proves stubbornly fixed at -1, then the mystery deepens still further. Why should the vacuum itself carry such a precise non-zero energy density? Why should its value be so small compared to theoretical predictions? Whether constant or changing, the equation of state is a riddle, and every new telescope and instrument is a key pressed against its lock. The universe is vast, patient, and silent, but through these efforts, humanity has begun to interrogate it with ever greater precision, like a student leaning closer to decipher the faded lines of an ancient manuscript. The new era of observation brings with it a paradox. For centuries, astronomy has struggled against scarcity to few data points, to few instruments, too little light captured from the depths of space. But now, humanity finds itself drowning in abundance. Modern surveys, like the Vera Rubin Observatory, Euclid, and DESI, are designed to record billions of galaxies, supernova, and lensing arcs, producing petabytes of information every year. Each image is not a picture in the casual sense, but a coded mosaic of measurements, redshifts, magnitudes, distortions, alignments. Within them lies the imprint of dark energy's hand on cosmic structure. The challenge has shifted. It is no longer a matter of gathering enough light, but of extracting meaning from an ocean of signals. Data streams pour continuously from observatories across the Earth, and soon from the void of space itself. Servers hum under their weight. Algorithms pass through catalogues of billions of celestial entries, searching for patterns too subtle for human eyes. In this flood, truths about dark energy are not hidden like stars behind clouds, but scattered like grains of sand across a desert that stretches to infinity. Each clue may be smaller, slight deviation in galaxy clustering, a faint irregularity in the light of a supernova, but collectively they form the only possible map toward understanding. Astronomers speak now of pipelines rather than photographs, of statistical fingerprints rather than individual objects. Science has become a matter of scale, where only through the combination of countless measurements can one detect the faint pressure of the cosmos accelerating outward. The mystery remains, but the instruments of inquiry have transformed into factories of cosmic information, where the question is not whether the truth is visible, but whether it can be distilled from the noise. It is here that a new ally has entered. The search, artificial intelligence, machine learning, once confined to the realm of language and commerce, is now woven into the fabric of cosmology. Neural networks trained on simulated universes can identify lensing patterns, separate stars from galaxies, and even reconstruct missing data from noisy signals. They are the apprentices of astronomers, capable of sifting through billions of observations in the time it would take a human to inspect a handful. More profoundly, they can search for correlations that no theory has yet predicted, where human reasoning relies on models built from physical laws. AI can expose unexpected structures hidden within the data, subtle drifts, rare anomalies, faint inconsistencies that might betray the presence of new physics. In the hunt for dark energy, this capacity is invaluable. The question of whether the equation of state W changes over time may not be answered by a single measurement, but by detecting a pattern that threads across many surveys. AI is uniquely suited to follow these threads, weaving together disparate data into a coherent picture. Yet, for all its promise, machine learning is not without risk. Its conclusions can be opaque, its reasoning a black box. Scientists must learn to balance the efficiency of algorithms with the caution of interpretation, ensuring that in the pursuit of dark energy they do not mistake artifacts of computation for cosmic truths. The frontier, then, is not only in the sky, but in the dialogue between human intuition and machine perception. Together, they form a new kind of observatory, one built not of mirrors and glass, but of circuits, codes, and simulations that mimic the universe itself. The mystery of dark energy is written into reality, but the deciphering now requires both human wonder and artificial cognition, entwined in the same pursuit. The revelation that most of the cosmos is composed of something unseen, unmeasured, and perhaps immeasurable casts a profound shadow over human understanding. For centuries, humanity has tried to chart the heavens as if the universe were a map awaiting completion, a puzzle whose final pieces would eventually lock neatly into place. Yet dark energy resists this dream. It is not merely a missing fragment, but a reminder that the picture itself may be far larger than imagined. To know that nearly 70% of all existence is driven by a force no instrument can yet touch is to confront a staggering humility. What does it mean to live in a universe where the dominant influence is hidden? It is as though human beings dwell in a vast cathedral of space, marveling at its stained glass and arches, while the very foundations beneath their feet remain unknown. The stars, galaxies, and planets, the totality of what can be seen are only the flickering candles in this cathedral, while the true architecture lies in shadow. Such knowledge does not diminish humanity, it redefines it. In this light, human fragility is both undeniable and profound. For all the achievements of science, the rockets hurled beyond Earth, the telescopes peering into the past, human beings remain like children standing at the edge of an ocean, their toes barely touching the surf while the depths extend beyond sight or comprehension. History offers echoes of this disquiet. There was a time when Earth was thought to be the fixed center, the unmoving anchor around which all celestial bodies revolved. To abandon that certainty was a wound to human pride, yet it opened the path to modern astronomy. Later, time itself was believed absolute, a steady metronome against which all motion could be measured. Einstein shattered that illusion, showing that time bends and flexes with gravity and speed. Now comes a deeper wound, perhaps the most humbling of all, that even the very fabric of cosmic acceleration is propelled by something nameless, ungraspable. Each revolution of thought peels away another layer of certainty, exposing the fragility of human assumptions. Dark energy is not the first mystery to dissolve old truths, but it may be the most radical. It suggests that reality is not simply unfinished in its details, but fundamentally strange at its core. Faced with this, humility becomes inevitable. Human beings are not masters of the cosmos, nor even central participants. They are witness-sized brief sparks of awareness in a universe ruled by hidden forces that may never yield their secrets. Yet, it is precisely this humility that makes the reflection beautiful, for it is not ignorance alone, but the courage to confront it, that defines what it means to be human. The haunting prospect that dark energy may one day dictate an end where nothing survives lingers in scientific speculation like a shadow on the horizon. Should its strength continue to grow, galaxies themselves will be torn apart, stars ripped from orbit, atoms dissolved into silence. The Big Rip, as it is sometimes called, offers an image not of fire or collapse, but of endless unraveling, where the very threads of existence are pulled apart until nothing remains. Even without such violence, the fate dictated by dark energy appears bleak. A universe of eternal expansion grows colder, dimmer, more empty with every passing eon. Stars burn out, galaxies drift beyond sight, and in time, all that remains is a thin mist of radiation in an infinite void. It is a vision of an ending, not with a bang, but with a fading whisper, the extinguishing of all memory. For a species tied to meaning, the prospect can feel unbearable. To know that everything cherished the stories, the songs, the achievements, carved into stone and steel will one day vanish into silence is to face the deepest vulnerability. Yet in this vision of oblivion, there is also a strange kind of beauty. For even if the universe concludes in silence, there was still the moment of light, the era when beings of flesh and thought dared to ask why. Dark energy does not only threaten to erase existence, it frames it. It places each human life against a backdrop of unimaginable scale, making every heartbeat every question, every gaze at the night sky an act of defiance against the void. The silence at the end does not diminish what came before. On the contrary, it makes it radiant. The universe began in fire, and it may end in stillness, but in the brief interval in between, consciousness arose, and with it the courage to wonder. Dark energy has become more than a physical enigma. It has become a metaphor for mystery itself. It is the unseen wind sculpting the fate of all existence, the invisible hand steering galaxies apart. For centuries, mystery has always retreated. Before the advance of knowledge, lightning was once the anger of gods, until it became understood as electricity. Disease was once a curse, until microbes revealed their hidden dominion. Yet dark energy stands apart. It is not simply is unknowable in a way that defies ordinary categories. It is not a thing that can be touched, nor a particle to be weighed, nor a wave to be measured in familiar terms. It is the silence beneath the music, the dark canvas upon which the stars are painted. And perhaps that is why it stirs something. Beyond fear, instead of despair, it invokes awe. To live in a universe that resists total comprehension is to inhabit a work of art rather than a solved equation. Each galaxy drifting outward is not merely a calculation, but a brushstroke in a cosmic mural, painted with a hand that will never be fully seen. And perhaps that is what compels humanity most, not the promise of answers, but the endless horizon of questions. Dark energy becomes less a barrier and more a beacon, a reminder that there will always be realms beyond understanding, and that this too is part of existence's poetry. The human story is shaped as much by what it cannot know as by what it can. Long before the telescope, before mathematics carved precision into the heavens, myths filled the sky with meaning. Constellations were woven into tales of gods, hunters, and monsters. The unknown was not emptiness, but a stage for imagination. Today, the unknown takes the form of dark energy, and though the myths have given way to equations, the wonder remains. There is humility in admitting that the greatest part of the universe lies outside grasp. Yet there is also strength in the act of asking, the act of measuring galaxies, building instruments, and writing theories is itself a declaration of resistance against silence. It is the insistence that even if the final truth is forever beyond reach, the pursuit still matters. In this way, humanity transforms the storm into poetry. The winds of dark energy may one day erase all things, but in the present they provide the most profound canvas for reflection. To look into the night sky and know that the faintest star is being carried away by an unseen tide is to realize that existence itself is a miracle of transience. Each breath, each thought, each moment of recognition is illuminated, not in spite of the darkness, but because of it. The unknown is not an absence. It is the stage upon which awareness becomes luminous. If history teaches anything, it is that. Each horizon of knowledge reveals yet another beyond. When Copernicus displaced Earth from the center, it was not the end of the story, but the beginning of a deeper one. When relativity and quantum mechanics dismantled the certainty of classical physics, it was not a collapse, but an opening. Dark energy may be the latest horizon, but it will not be the last. Its presence reminds humanity that mystery is not a flaw of understanding, but an eternal companion of existence. To demand a universe without mystery is to demand a universe without depth, without beauty. The storm, invisible though it is, becomes a kind of teacher. It whispers that not all truths can be held in equations, that wonder itself is a form of knowledge. Science and philosophy converge in this recognition. Where numbers end, reflection begins. Where equations fail, poetry continues. And so the quest does not diminish with uncertainty, it flourishes. It is the paradox of knowledge that the more is discovered, the greater the unknown becomes. Dark energy is not an obstacle to comprehension, but the ultimate invitation to humility and imagination alike. This humility may be humanity's most enduring legacy. For all the violence, the wars, the fractures of history, there is also this, a species that looked into the void and asked, "No other creature on earth has traced the galaxies or wondered at their fate. No other voice has risen against the silence of an expanding cosmos." Dark energy becomes the mirror in which human identity is revealed, fragile yet luminous. It shows that meaning is not granted by permanence, but by inquiry. Even if the universe ends in silence, the questions asked within it echoed beyond their answers. The courage to look into the abyss and not turn away may be the most extraordinary act of all. And so, when the night grows quiet and the stars drift farther apart, what will remain is not despair, but memory, that in the vast expanse there was once a species who named the darkness, who sought the unseeable, and who found in the unknown not terror, but wonder. The universe began in fire and may end in silence. But in between, there was this fragile moment of light and interval, when awareness bloomed and asked the greatest question of all, why?